Sorry, just one second. You just let me know when.
Yes, so we can begin. So welcome everybody to the last talk of the day. We have Gordan from Fermilab and University of Chicago, and we talk about observable CMB BB modes from cosmological phase transitions.
Great, thank you very much. Yeah, and I'm very excited to talk about a recent paper with my great collaborators, Kyla Green, Aurora Ireland, and Yushin Tsai. And as you can guess from the title, it's about the polarization signals of B modes in the CMB, but from physics that is not inflation. And so I'll start with just a little bit of an overview of tensor perturbations in B modes to get everybody on the same page. I'll review just the basics of what we expect from inflationary predictions with regard to tensor modes that give us B modes, and then I'll talk about how phase transitions might give us a different kind of signal, which is interesting and complementary. So, getting started with a familiar story. Cosmological perturbation theory is generally the program of taking Einstein's equations in general relativity, which we usually think about in a cosmological setting as representing perfect fluids of different equations of state. But in perturbation theory, we deviate away from isotropy and homogeneity with small fluctuations. These are small fluctuations both in the metric and in the stress energy tensor, which acquire some positional dependence, which now has scale variant as opposed to invariant properties. And we typically think about this in terms of two basic quantities in most cosmological settings. We think about this in terms of a scalar perturbation, which morally corresponds to isotropic stretching at different points in spacetime, and tensor perturbations, which are anisotropic stretching, so they give rise to some kind of strain at every point in spacetime. Now, for CMB polarization, before the first atoms formed during recombination at redshift about 1100, electrons and photons are tightly coupled through the process of Thomson scattering. And so here, schematically, if a photon comes in with some polarization and scatters an electron near the surface of last scattering, right before hydrogen forms, the Thomson cross-section has some polarization dependence when we think about it as an angular dependent quantity. And because this cross-section is sensitive to the polarization states, this offers us a complementary probe of the universe at the time of recombination. In addition to the usual temperature anisotropies, we get information about polarization anisotropies from Thomson scattering. So if there are temperature variations in the photons, those will be imprinted in the CMB as polarization anisotropies through their interactions with electrons at the surface of last scattering. And so the foundational work connecting B modes and tensor perturbations traces back to the mid 90s. So we have foundational papers from a number of giants in our field. And the important thing to note about this is that CMB polarization can only arise if we have a quadrupole moment. And so to engineer a quadrupole moment, what we need from the perspective of some position in space-time, here we have an electron positioned at the origin of some coordinate system, and it's surrounded in a bath of CMB photons right around the time of last scattering. And if we have a quadrupole, it corresponds to a configuration somewhere in space where the photons happen to be cold along one direction and hot along an orthogonal direction. So this is kind of like having a quadrupole moment. And what this means is that when you transmit a photon along the z direction and you take out the polarizations that are orthogonal to the z direction from both contributions along the x and y direction from which they were originally scattered, the transmitted polarizations are not isotropic along the direction of motion or along the directions that are orthogonal to motion, and that corresponds to a polarization. The polarization signals we get can be either of a parity even mode configuration or a parity odd configuration. And the important thing about the parity odd configuration is that it's something that can really only arise from genuine tensor perturbations. So the E mode polarization can arise from a variety of sources, but it was shown that in the mid 90s that the parity odd configuration is special, so that we get different kinds of swirly patterns of polarization around hot and cold spots. And that's interesting. That can be separated from data in a characteristic way and gives us information about gravitational waves that were present around the time of last scattering. So, how do we think about this in terms of its connection to fundamental physics? At this point, we haven't said anything about the origin of the gravitational waves, but what we would want to do in order to connect this to some sort of fundamental input, to connect the tensor perturbations themselves to some power spectrum of gravitational waves, we write down a two-point function. So here, Hij is the input tensor perturbation. The two-point correlation function of this quantity in momentum space can be written in suitable normalization in relation to some quantity P sub h. So P sub h is the tensor power spectrum, and this is the usual relationship between a two-point correlation function and a power spectrum. Here it's normalized in such a way that P sub h is a dimensionless quantity. And typically what we would do in order to extract CMB observables is we define an angular power spectrum. So we take some power spectrum in momentum space and convolve it with a kernel which is defined in terms of a multipole expansion and a suitable normalization such that the quantity d sub LBB has units of microkelvin. So we multiply by the CMB temperature T naught squared. And this quantity now has two inputs. So there's some very long and not terribly illuminating expression in F sub L, which contains integrals over a visibility function that knows about the Thompson scattering cross-section, about transfer functions that tell us about the growth of perturbations due to the expansion of the universe. It knows about how we project onto the sky, and importantly, it's an artifact of having done a multipole expansion. So we're considering for each L some characteristic angular scale. The other quantity here contains primordial information. So this genuinely has to do with how the gravitational waves were generated in the early universe. And this is the part of the expression that's calculable from fundamental physics. And it's ultimately what we're interested in. And so let's talk a little bit about how we typically think about this quantity in the context of cosmology. We'd like to know what the origin of the gravitational waves is. And so the formalism that will follow for the rest of this talk is really based on the Rubikov textbook, which gives an excellent treatment of exactly how we connect some fundamental input that gives us a power spectrum to an angular uh, separation of scales when we look at temperature and polarization anisotropies in CMB data. So the usual way that this works is we make some prediction based on our favorite inflationary theory, and that gives us a prediction for P sub h. So we care a lot about inflation because inflation solves a lot of problems for us. We think about this as an epoch of exponentially fast inflation, whose main predictions are related to the Hubble rate during this period of exponentially fast inflation. And it solves many problems for us. It solves the horizon problem. So why are different small patches of the sky, as we observe them today, apparently causally disconnected from each other if we just propagate the universe back to the surface of last scattering? That standard cosmology would not give us a coherent explanation as to why different patches of the sky on scales larger than about 2 degrees are drawn from the same statistical distribution, even though light didn't have enough time to travel between two regions that are larger than that in terms of angular separation. It also solves the flatness problem because Friedman, Robertson, Walker cosmologies are allowed to have spatial curvature, and spatial curvature redshifts much more slowly than any other component in the universe, more slowly than radiation or matter or something more exotic like kination. And as a result, it would tend to become dominant. It's an attractor solution that the universe should be dominated by curvature, even though it's observed to be essentially flat. Um, Inflation also solves the monopole problem. If you believe in your guts that nature is unified at some large, high temperature scale, that we would generally produce a lot of magnetic monopoles, which are not observed. If we have a period of exponentially fast inflation, all of these problems are solved. It changes the causality structure of the early universe. It flattens the universe by getting rid of the non-zero spatial curvature, and it dilutes any previously present population of magnetic monopoles. And as an afterthought, after solving all of these wonderful problems for us, it was realized after inflation was originally proposed that it happens to generate the scalar perturbations that are responsible for structure formation, the perturbations in the CMB, and also gives rise to tensor perturbations. So in one shot, it does many different things, which is why I would think we largely believe that inflation happened in our past light cone. And inflation can be characterized by some very simple parameters that are ultimately related to the shape of a scalar potential of the field that's driving cosmological inflation. So you can get the nice properties of inflation if some initial scalar field, the inflaton, is displaced from its minimum and sits on top of a rather flat potential while the universe is inflating. And due to quantum fluctuations, there are perturbations that we generate on a large variety of scales. They're typically characterized by slow roll parameters, which are given by the first and second derivatives of that scalar potential. So it's a very simple class of models if inflation is only driven by a single field. So this is the simplest case. And the scalar perturbations depend on a combination of the Hubble rated inflation h sub I and the first slow roll parameter epsilon. The spectral tilt that inflationary theories predict is a linear combination of the two slow roll parameters, and it's essentially a prediction of a scale invariant spectrum. So ns minus 1 is approximately 0, and so you get scalar perturbations with almost equal power on all scales that are observable in the CMB. And this is a measured quantity, so we've measured the amplitude of scalar fluctuations in the tilt, but the amplitude depends on two parameters which are currently unknown. However, the tensor perturbations depend really only on one perturbation in the initial in the amplitude. The amplitude really only depends on the Hubble scale at inflation, and so if we could measure the tensor perturbations, we'd have a nice prediction of what the tensor to scalar ratio is, and that would complete this picture since we've already measured the scalar ones. Importantly, both the scalar and the tensor perturbation spectra from inflationary predictions are essentially scale invariant. And so the input quantity that goes into making the predictions for the temperature inhomogeneities and the polarization inhomogeneities are basically flat functions as a function of the momentum parameter k. When we convolve the power spectra with regards to the angular power spectrum, we make the prediction of the angular power spectrum by convolving the input power spectrum in momentum space with the appropriate kernel that tells us how the anisotropies break down on different angular scales. We see a variety of different predictions. And the important one that I'm going to focus on for this talk really comes from the B-mode prediction. So these are the bottom two blue curves. I don't know if you can see my cursor because I can't. But the blue curves that are the bottom two, parameterized by the value of R, the tensor to scalar ratio, are the gravitational B-modes that are predicted in inflationary theory. So the upper value of this curve gives us something that's roughly at the current limit of what inflationary theories predict, where you're basically saturating the data points of the measured polarization that we've already seen in the CMB. Of course, the measured polarization is consistent with lensing B modes. These are the foregrounds, where E modes are converted to B modes due to astrophysics and other cosmological post-processing in the later universe, due to, say, lensing or dust and things like that. And so far, we have no non-zero signal of any inflationary contribution or any other contribution for that matter. So we can set limits. So the limit at 0.03 is currently what we could constrain. And of course, if you make a different prediction based on a different value of R, what you really do with inflationary theories is you move the prediction up and down, but not left or right. So there's a universal family of predictions that single field slow roll models tend to predict. And so we're looking for templates of the form of these blue curves and asking what's the value of R based on how far up or down we can go given current values of the experimental sensitivity. So the inflationary curves are down here. And we'd like to know, for our purposes, whether that's the only option, because there's this lore in our field that tensor fluctuations are really a way of providing a conclusive verification of the theory of inflation. So this is something we see even in very prominent parts of the literature. And so the question that I'd like to address in the rest of this talk is whether inflation is the only viable way to make B-modes. Because so far, although inflation makes a very compelling prediction for exactly what we would expect for the B-mode predictions that we can compare to CMB data, there's nothing about the formalism that requires it to really be an inflationary prediction. Any theory that predicts some power spectrum of tensors with support on the scales that the CMB can measure would also be able to make a non-zero prediction there. And so the question is, are there candidate theories that can rival the intensity of inflationary predictions on the scales where we're poised to make measurements going forward? And so now I'd like to pivot to talk about how phase transitions from some hidden sector in the early universe might complicate an inference of B modes. So if we see something, does it obviously mean that we're seeing inflation? So it's interesting to me that cosmological phase transitions were studied in their cosmology context as sources of stochastic gravitational wave backgrounds in around the same time that people were making connections between gravitational waves and CMB polarization, and in some cases by some of the same people. So you might notice, for instance, that Kamienowski and Kozowski were also on my earlier slide of people who were making foundational connections between B modes and gravitational waves. But it's interesting to me, and we were very surprised when we first started thinking about this question, that someone didn't already work this out 30 years ago. And I think one of the reasons for why it hasn't been worked out, at least not to our knowledge, and of course, if you do know of a paper of someone working this out earlier, we would like to know because we didn't find any. I think the answer for why this was kind of a neglected topic is that in the mid 90s, our theory priors about what could be going on in the very early universe were not really focused on hidden sectors and certainly not focused on relatively late time phase transitions. That if you're talking about phase transitions in 1993, you're typically thinking about something like the electroweak phase transition, which happens at a very high temperature when the Hubble scale is very small, such that if you were to produce gravitational waves, they would be extraordinarily high frequency compared to what we might expect to observe in the CMB. And similarly, you might also think, okay, there could be more exotic phase transitions due to grand unified phase transitions or leptogenesis. All of these are at very high scales. Even the QCD phase transition picks out the MeV temperature scale, which still corresponds to an astonishingly high frequency compared to what we tend to observe in the CMB. So I think that the first papers that were asking questions about gravitational waves from cosmological phase transitions thought that it would kind of be a hopeless enterprise to ask what the B mode predictions would be due to this scale separation. But I think it's fair to say that over the past 10 years in particular, as we've come to learn quite a lot more about the CMB and have broadened our priors about exactly where new physics happens to be. We haven't seen a lot of new things at the LHC. We haven't seen things like conventional WIMPs at direct or indirect detection experiments. We've come to appreciate that whatever new physics is out there to solve the big problems in fundamental physics is probably in a more surprising place. And so we've started to ask questions about, well, what happens in the much later universe? And I think this question is much sharper now that we're observing things like gravitational waves with interferometers at LIGO and soon with LISA, especially now that we're observing gravitational waves with pulsar timing arrays, which are pushing us to much, much lower frequencies. Um, and uh, it's worth asking the question of what could happen if a late time phase transition were to happen in a hidden sector, so not involving standard model fields, but it's happening in a hidden sector that's a small fraction of the energy density in the early universe. So the standard model doesn't provide us a candidate for how to do this. All the phase transitions that we know and love are believed to be crossovers, at least at face value, unless there's new physics involved. But they're also at much higher scale, so they're not going to be relevant for us in the study of CMB phase transitions. Um, First order phase transitions that give us gravitational waves typically proceed through bubble nucleation, so there's some maybe scalar field or some epoch of confinement that's happening with some other fluid that's just a spectator for our purposes. And you get gravitational waves from the collisions of those bubbles as they expand. You also get them from sound waves, from turbulence, maybe from particle production. And there's some characteristic phenomenological parameters that we tend to write down to characterize the properties of the spectra of these phase transitions, at least in terms of their gravitational waves. So what I'll talk about going forward will be written in terms of these parameters. So T star is going to be the temperature of the phase transition. And I want to be very clear, this is not the temperature of the fluid itself. This is just going to be a proxy for the time of the phase transition. So this is the temperature of the universe of our photons at the time that the phase transition takes place. And that's going to be true of any quantity that happens to have a star on it. So I'd like to be very clear about that because I'm not talking about the temperature of the fluid itself. These are going to be temperatures of photons. And of course, the hidden sector is completely decoupled from our photons. Um, and will generically have very different thermodynamic properties, typically at a lower temperature, if such a thing were to describe this other sector. Beta, or beta inverse rather, is the duration of the phase transition. So this is the inverse of the bubble nucleation rate. Alpha is going to be some parameter that characterizes the energy density of this other sector relative to the energy density of radiation in the standard model. So this, for our purposes, is going to be a parameter much, much less than 1 because we're going to be thinking about relatively late time phase transitions. And there's going to be some parameter kappa which characterizes the efficiency of gravitational wave production relative to, say, the gradient energy of the bubbles that are colliding. So conservatively for our purposes, but also conveniently because this is the one that's most robustly calculable, we're only going to consider gravitational waves from the bubble collisions themselves. We're going to be leaving money on the table. We're not going to be considering things that we know are likely part of the story, things like sound waves and turbulence and particle production and so on. And so we're interested in the analogous quantity that we were considering before, the two-point correlation function of tensor perturbations as they're related to some power spectrum that we can calculate from fundamental physics. So during the phase transition, the quantity that we use in order to calculate the power spectrum, so Hij, this is the transverse traceless strain that is produced in gravitational waves, we can relate that to some source term that knows about the microphysics of the phase transition. So here I'm defining some quantity x, which is dimensionless. It is the momentum of the gravitational wave multiplied by the conformal time tau. So this is a dimensionless quantity, and primes are related to, or primes define derivatives with respect to the quantity x. If you take the equations of motion of linearized GR and you express them in terms of this quantity, you get this expression. It's just the equation of motion in the presence of a source term, and A is the scale factor of an FRW universe. Here, if the phase transition is fast compared to a Hubble time, we can neglect the effects of expansion, and A star is just a quantity that enters into the normalization when we write things in conformal time. This follows the notation of this wonderful Caprini et al. Paper from 2009. The quantity that sources gravitational waves is the transverse traceless stress energy tensor, and we can write that in terms of its own power spectrum. So the correlation function of the transverse traceless stress energy tensor gives rise to a quantity that's analogous to the the power spectrum that we're ultimately interested in. So this is going to be proportional to the quantity curly p sub h that lives in what we ultimately want to calculate. And this is going to be a white noise power spectrum on large scales. And it's importantly very causality limited on large scales that are larger than the cosmological horizon. And so we'll revisit that issue in just a moment. And importantly, we can solve this using the method of Green's functions while the source is turned on. And so there's a large literature, again going back 30 years, that characterizes the mathematical properties of the source term itself. And we're interested in the Green's function solution that tells us exactly what the strain is at the time that the phase transition completes. So there's some final time, some x sub f that we're interested in. That lives in the integration limits of the Green's function solution. So after the phase transition, the tensor perturbations evolve according to the homogeneous equation of motion, which now has to take into account the effects of cosmological expansion, which is why there's a gravitational term on the left-hand side and why there's a zero on the right-hand side. We can solve the general solution in terms of two modes. There's a growing mode and a decaying mode characterized by some amplitudes A and B. And we can relate those to the Green's function solutions that are realized at the time that the phase transition completes. We can satisfy boundary conditions, and this is all consistent with the way that this is typically treated in the literature, including the formalism of the Caprini paper from the previous slide. Now, we have everything to calculate exactly what we want. Once we have the solution to Hij, the tensor perturbation, both during and after the phase transition, we can define a correlation function in momentum space. That correlation function relates to the power spectrum, the dimensionless power spectrum of tensor perturbations, and ultimately that can be convolved with a kernel in a multipole expansion to give us the angular power spectrum suitable for comparison with CMB data. Now, there's some distinct scaling regimes that we're going to be interested in. So the bubbles that are nucleated during a phase transition have some characteristic size and separation, and there's a duration that's associated with their nucleation. Those are all scales that live inside the horizon. The horizon itself is a relatively large scale, so waves cannot propagate on scales that are larger than the horizon. The horizon itself is limited by causality, such that in position space, the correlation length on scales that are larger than the horizon has to vanish. Okay. The first regime that we're going to be interested in is on very, very small scales. So if we're interested on scales that are small compared to the bubbles themselves, and certainly much smaller than the horizon itself, that corresponds to values of k tau that are much, much greater than the quantity beta over h. Again, whenever there's a star, that represents some quantity at the time of the phase transition. So here we're defining these quantities in terms of the conformal time at the phase transition's end and the Hubble rate at the end of the phase transition. So beta is a characteristic scale representing the inverse duration. So beta over h, typically a number bigger than 1, is going to be a comparison of the nucleation rate relative to the Hubble expansion rate. So we expect it to be large compared to 1. And if we take k to be large, we're going to very, very large, very, very small scales. So this is taking the limit that's much, much smaller than both the horizon and the bubbles. And so in this limit, there's a standard formalism for exactly how to calculate the scaling with regard to wave number k, and there's a very nice paper by Gino and Takimoto from 2016 that characterizes exactly what the properties of this spectrum are. Without getting into the details of how this is calculated, it boils down to being a double integral with respect to time. And they write this down in terms of a very helpful phenomenological fitting function, which has a characteristic momentum dependence in different regimes. So what's important about the sub-bubble and sub-horizon scales, the smallest scales in the problem, is that the dimensionless power spectrum has the scaling k to the minus 3. And so we are on the right, in the upper right of this plot, when you're to the right of the scale k sub p characterizes the bubble scale, and we're going to scales much, much smaller than that. So here we're falling as k to the minus 3. Now, we can go to the opposite regime where we're considering superhorizon scales, which are limited by causality. And on these scales, we get the opposite behavior. So the correlation function in position space is limited by causality. And if that function has no support outside the horizon in position space, its Fourier transform has a characteristic white noise tail. And that white noise tail has a scaling of k to the plus 3. This is to the left of the peak scale that characterizes the bubbles themselves. It's related to the same fitting function that we saw in the Gino and Takamoto paper, but with some additional powers of momentum. It's still related to the same phenomenological parameters that characterize how loud the phase transition is. So alpha, beta, H star, kappa, and so on. These enter in with a slightly different combination, but all of their products still determine exactly how loud the phase transition is in this regime. Now, the intermediate scale is the most complicated one. This is a scale that's larger than the bubbles themselves, but is smaller than the horizon. And this is a scale that's fraught with the largest amount of theoretical uncertainty, where numerical and computational methods are the most important. And this is also the one that's most model dependent. Now, depending on which phenomenological parameters you're considering, you might have much, much greater contributions from things like sound waves or turbulence or wherever else is defining the problem itself. So here we're going to be maximally agnostic. Here, we're going to take the scaling regimes that we trust, that are well calculated and analytically under control, and we're just going to match them. Now, this is a matching that is on some level arbitrary. We're going to pick a scale called a breaking scale, and we're going to enforce continuity across these two regimes, because if you take the functions that define the green curves here on large scales and small scales, they don't exactly match up at the peak bubble value. But those scales, those functions themselves are valid in their appropriate regimes, both in terms of their scaling behavior and in their amplitude. So to match them, we're going to do the simplest thing and draw a straight line in log space. Of course, this is the greatest source of theoretical uncertainty. And in our paper, we comment on exactly how sensitive the results are to making different modeling choices here. Fortunately for our purposes, in the regime where we're dominated by one or the other of these scales, either the very largest or the very smallest scales, this modeling choice does not matter. But of course, it does matter if the peak is inside the window within which the CMB is most sensitive. So your favorite model will likely receive some important corrections if the peak is relevant for making predictions that are relevant for the CMB, but outside of that, it's not particularly sensitive. And so when we put all of these ingredients together and we ask what happens when there's a relatively late time phase transition in a hidden sector, we make a prediction for the tensor power spectrum, which serves as an input to the angular power spectrum. And there are certain modes, and I apologize, the parameter k here should really be in units of inverse megaparsec. Different choices of temperature and the photon temperature at the time of the phase transition and what fraction of the universe this hidden sector consists of will make different predictions in this plane. And we can contrast that with what inflation predicts, because in terms of the same quantity, inflation predicts a straight line. Inflation says that we should expect a relatively flat input power spectrum, and that flat input power spectrum is what defines the shapes of the angular power spectra that we're used to seeing in writing down the angular power spectrum. Importantly here, our predictions are not scale invariant. They depend very importantly on the different regimes. There's a peak frequency that is set by the size of the bubbles and by the Hubble rate at the time of the phase transition. And we have some very characteristic but highly non-scale invariant behavior, both on much larger and much smaller scales. So when we convolve everything with the kernels that tell us what the angular power spectrum is, we have these predictions. So here, again, the blue dashed curve is what inflation predicts for some value that's near the boundary of what we're currently sensitive to. And here's a phase transition in green on the upper plot, which is what you would get if a phase transition were to occur at cosmological temperatures of 1 electron volt in a hidden sector that is about a 10 to the minus 5 fraction of the universe in terms of its energy density. And you'll notice that it makes a very different prediction for the angular power spectrum when we take the ratio of the inflationary prediction to the phase transition prediction, which is what the bottom panel predicts. So there's some characteristic deformation that we get. And the most interesting thing for me about this plot is that on large scales and on small scales, we exhibit very different behavior qualitatively. So on the smallest scales, going to the right of the plot, we see an enhancement because the peak of the inflationary curve, which can't change, it just goes up and down depending on different values of R during inflation. Um, the blue curve is always peaked at about multipole values of about 100. Our curve, the phase transition curve, generically peaks at values that are closer to 1,000 or a few hundred. So it's shifted to smaller scales. There's typically more power if you normalize to some equivalent value. Here, there's more power on large scales and less power on small scales, reflecting the K scaling of the dimensionless power spectrum. Now, importantly, on the largest scales, the CMB characteristically predicts a reionization peak. So that's the bump at very low values of multipole moment. Oh, sorry. That's the bump at very low values that is related to the physics of reionization. So normally during the CMB, Thomson scattering stops being an important contribution at redshift of about 1100. But at redshifts of about 10, when the universe is reionized and the first stars form, and you go from being a universe of largely neutral hydrogen to a universe of largely ionized hydrogen, you reactivate Thomson scattering. And that reactivated Thomson scattering gives you an additional effect in the CMB itself, which is, of course, present at this time. And this is an effect on larger scales because the Hubble rate or the Hubble volume is bigger at this time. So you get this bump, but that bump still is convolved with the input primordial power spectrum. The gravitational waves are still there from inflation, and they still have a scale invariant character. It's just that Thomson scattering is turned on again on the large scales where the tensor perturbations are present, and therefore you get this bump. But in our case, you don't get the bump because on these larger scales, you're in the superhorizon regime where the scaling is k cubed. And as you go to small values of k, you're affecting the small l part of the dimension of the angular power spectrum, and it kills the reionization bump, meaning that there are important discriminating properties with regards to these two different predictions. Now, if you consider a different phase transition parameter, you're pushing the phase transition predictions to larger and larger multipoles, but with the same qualitative behavior that the reionization peak is gone. Here we're comparing to a different normalization of the inflationary power spectrum, but it has the same inflationary shape. The phase transition here has a somewhat different shape because you're now, in this case, sensitive to a different part of that triangle that characterizes the phase transition input power spectrum. So if you sort of put different phase transition predictions on the same plot here, here we're varying the time at which the phase transition happens. So T star is the temperature of the standard model at the time of the phase transition. And we're comparing it against two different inflationary predictions, which are the black curves. And you'll notice that the phase transition predictions are self-similar for very large phase transition temperatures corresponding to the lower values shown here on the plot. But as you go to later and later times, corresponding to lower and lower temperatures and getting more and more blue in this temperature map, what tends to happen is that you start to be sensitive to the peak of the input power spectrum. And as a result, you get some changes in the shape that we predict. But that's really the only difference. In all cases, you tend to predict larger power at larger multipoles and less power on smaller multipoles. Now, for complementarity, if you were to now ask for the same phase transition parameters, what would the predictions be if you were to translate this into an expression for omega GW, the thing that we're typically used to seeing for stochastic gravitational background predictions? You get these curves. So the green and the red curves here are for the same exact benchmarks that we were looking at on earlier slides, and the blue curve is one of the inflationary benchmarks. So there's the possibility that some of the smaller scale contributions are visible or detectable with future probes like this square kilometer array. Um, but they're typically far outside the reach of something like LISA, and so this is a new way of probing stochastic gravitational wave backgrounds at frequencies that we're not used to thinking of as being accessible, but they are accessible in the CMB for suitable choices of parameters. So I'll end it here just by flashing a couple of conclusions. And so the most interesting thing for me personally is that there's a qualitative point here, and that if we discover B-modes at a single scale, the way that we might have thought we had discovered B-modes back in 2013 when BICEP announced a discovery which was later found to be due to foregrounds and not due to primordial sources, if we really only discover it at one angular mode, it's not obviously inflation. It could be something else. It could be a signal due to a phase transition. Now, it's obviously new physics if we could eliminate contributions from lensing and foregrounds, which we regard as standard model predictions. But it's not a smoking gun for inflation unless you could really characterize what the shape of the prediction itself is. And so it's important to measure it on a variety of different scales with sufficient accuracy to test the hypothesis that the input power spectrum is scale invariant or not. The argument that we've made here is conservative and generic. We've only considered um, the alternative prediction from bubble collisions during cosmological phase transitions, noting that there are generically other contributions from things like sound waves and turbulence and so on. Of course, this has to be a hidden sector phase transition because the standard model can't give you any phase transitions that are first order or that could happen at the late times that we need. And it's important also to note that you could turn this argument around and say, because B modes are probes of gravitational waves due to phase transitions, you can use B mode data, both present and future, to constrain the parameters of cosmological phase transitions or other sources that happen to have similar kinds of spectral shapes. And so that's something that we're working on now with experimentalists from the SPT collaboration. So stay tuned for another paper that we hope to have out by the end of this year that actually uses the likelihoods of existing experiments to place limits on the parameters